Hi guys, welcome to a lesson of partial differential equations. So in the previous class, we discussed about the eigenfunction expansion, sign expansion for the Dirichlet boundary condition problem with the non-homogeneous heat equation with a time-dependent heat source. And now in this class, we are going to discuss cosine expansion for Newman boundary conditions, because we know that whenever we are going to meet with Newman boundary conditions, then we generate a eigenfunction that is the function of cosine, right? So here is the given equation, that is a non-homogeneous heat equation with time and space dependent heat source. All right, this is heat source, and these are the Newman boundary conditions. So we are going to use the cosine expansion for the solution of this problem. So let's move to the solution technique. Technique is same as the previous method, that's for sign expansion. All things are same, just the difference is the eigenfunction is different. There we use sine n pi x over L as eigenfunction, and here we are going to use cosine n pi x over L as an eigenfunction. And then we know that this is a cosine Fourier series, therefore we have a naught t as well, right? So Fn is same 2 over L times the integral of the product of the heat source with cosine n pi x over L. That is the eigenfunction. So we can write that the eigenfunction is cosine n pi x over L in this case, right? So this is the eigenfunction for Newman boundary condition. And for F naught, we have 1 over L times the integral of the heat source. Now for f of xt is equals to f naught t plus summation fn cosine n pi x over L. Then we will generate a family of differential equation, that is ordinary differential equation of first order. So here is the phenomena a naught prime plus sigma this differential equation times cosine n pi x over L is equals to f naught plus sigma fn cosine n pi x over L. So we can see that the idea is similar, only the change is the change in the function, right? Eigenfunction. So a naught prime will be equals to f naught, and this equation will be equals to this fn, right? In this way, we will construct the family of ordinary differential equations. So we can say this is equation 1 and this is equation 2. Because here a naught is independent, we can solve it independently, and for an we can generalize the solution, right? So here we can see that a naught of 0 will be equals to 1 over L times the integral of the initial condition, that is u naught x dx, and an is equals to 2 over L integral the initial condition with the product of the eigenfunction cosine and pi x over L, right? So let's move on to an example and start with the example. Given that ut minus uxx is equals to xt, so this is the heat source we have that makes the equation non-homogeneous, and these are the Newman boundary conditions, and we need homogeneous boundary conditions. So here we have the homogeneous boundary conditions, right? So we can proceed with the eigenfunction expansion, and this is the initial condition, right? So f of xt is equals to xt, and the initial condition is equals to 1. Therefore, f naught is equals to 1 over L, that is 1, times the integral of the function of xt dx. So from this, we get 1 over 2t. So this is our f naught. We will use it in the latter part. Then we have fn, that is 2 over L. So L is 1 here. and integral of the product of the function of xt with the eigen function, that is cosine and pi x over 1. All right, so from here we can integrate the function and we will get this solution. Here is the integral and we'll apply the initial conditions to get this form, right? So when we will simplify it, we will get here, you can see that fn is equals to 2t over n square pi square times -1 power n minus 1. So it will lead to -4t over n square pi square for odd ends and 0 for even ends, right? So we already know all this stuff. We are using it at the various stages in various problems, right? So now a naught of 0 is equals to 1 over 1 times the initial condition times dx, that is given as 1. This is the initial condition. So we'll integrate this, we will get 1 by applying the initial conditions. Then we'll find an of 0, that is the initial condition for n, and 2 over 1 times the initial condition with the product of cosine and pi x over L, that is 1 in this case, right? So we'll get 2 times sine pi x over n pi, then apply the conditions. We'll get 0 because sine and pi is 0 and sine 0 is also 0. So the initial condition for the family an will be 0, right? Now we can construct the ordinary differential equations with the initial conditions and we'll solve. So we discussed that a naught prime is equals to f naught, and we have the initial condition for a naught here, right? This is f naught. This is f naught. We calculated, and a naught of 0 is equals to 1. This is the initial condition. We will solve this equation. This is a first order equation, very simple, and we formulated this answer for a naught, right? And then we have the family of an. So an prime plus n square pi square an is equals to -4t over n square pi square for all n is equals to odd 1, 3, 5, and so on. All right, so this is a first order linear differential equation. We have the integrating factor e to the power n square pi square t, multiply with the equation and solve as we did for the linear equations, right? So here we solve this equation, we get this solution, and this is the final solution that is generated from this equation. In fact, this is the general solution, so we have to apply the condition to find this c, right? Now we'll apply the initial condition that is given, an of 0 is equals to 0. By applying this condition, we will get this c is equals to -4 over n power 6 by 6, right? So here is the particular solution for an. Now we have to construct the solution for u of xt, and here we can put n is equals to 2n plus 1 because we know that n is for odd terms. So 2n plus 1 represents all the odd terms, right? When we will put 0 here, we will get 1. When we will put 1 here, we will get 3. When we will get put 2 here, we will get 5, and so on, right? Therefore, we are replacing n with 2n plus 1 everywhere. So we can see here that we have replaced n with n plus 1. And here also we have to write 2n plus 1. So it will be 2n plus 1 whole squared. Let's remove this first. It will be 2n plus 1 whole squared pi squared t. Right, so now this is okay. So here is the general solution, particular solution for this non-homogeneous heat equation. That is t squared over 4 plus 1. That was our a naught. This is a naught. right? And this whole is an times cosine and pi x over L with summation, right? So an we calculated, that is this whole function. This whole function is an, and then multiplied with the eigenfunction of this problem. This whole is our an, all right, and we multiplied by the eigenfunction to this problem, that is cosine and pi x over L. So L is 1 in this problem, and for n we substituted 2n plus 1 because of the odd terms. Therefore, this is the final solution for this problem, right? So now we are moving to the next problem. That is example 2, and here we can see that this is the heat source at cosine 2 pi x, and these are the Newman conditions, and initial condition is equals to 0. So it's a simple problem. We just need to find Fn. For Fn, we know that we have to find Fn and F naught, right? Because this is cosine expansion for the Newman boundary conditions. So Fn is equals to the function of xt times cosine n pi x. That is the eigenfunction for this problem. And we know that e to the power t will treat as constant here. So we'll move outside the integral. And when we will solve this cosine 2 pi x times cosine n pi x, so when n is not equals to 2, we will get 0, right? This integral will be 0. And when n is equals to 2, then we will have the solution for this integral. Here we have solved that, right? So it will be cosine 2 pi x times 2 pi x cosine square 2 pi x. So we can use the identity of the angle 1 plus cosine 2x over 2. Therefore, this is 1 plus cosine 4 pi x over 2. And then we solve the integral and applied the limits. So here we can see that f2 is equals to e to the power t, right? Because sine 1 is 0 and sine 0 is 0. So this whole will be 0. Therefore, we'll only left with f2 is equals to e to the power t, right? f2 is because of this 2, right? This is n. So when n is 2, so it will be f2, right? So this is f2. Now for f naught and all other fn's are 0 for n not equals to 0 and n not equals to 2. Because for n not equals to 0, we are calculating this f naught, right? So for f naught, we have the formula 1 over L times f of xt. Yes, f of xt times the, sorry, not f of xt. There's something we have to check. So this is f naught. For f naught, we know that this is 1 over L times the function of xt times dx. So L is equals to 1. Therefore, outside we have 1 outside the integral here, right? And this function of xt. So et, we can move outside the integral and we will apply the condition on this integral. So it will be 0 because sine 2 pi is 0 and sine 0 is 0. Therefore, f0 is also 0, right? So now we'll calculate a naught and an and a2. So a naught is equals to 1 over L times the initial condition integral dx. So this is equals to 1 over 2 because the initial condition is given as x, right? Or we can check for the initial condition. So the initial condition is x here. So by mistake, I write 0. This condition is x. This is x, right? So that's why here we are solving for x, right? So a naught of 0 will be equals to 1 over L times the integral of the initial condition with the limits. So you'll get 1 over 2, right? Then we will solve for an. So an is equals to an of 0. It's equals to 2 over L times the integral of the initial condition with the product of eigenfunction. We will solve the integral and we will get this result, right? So it's negative 4 over n square pi square for odd ends and 0 for all other ends, right? So here a naught prime is equals to 0 because f0 is 0 and a naught of 0 is equals to 1 over 2. Using the initial condition, we'll solve the differential equation. So we'll get a naught of t is equals to half. Then we will solve a2 prime plus 4 pi square an is equals to e to the power t. All right. And so a2 of 0 is equals to 0. We can see that a2 prime, we are using this equation because f2 was equals to e to the power t. We solve for this, and for all other ends it was 0, right? So that's why we are solving for a2. So we'll solve it using this condition. We will get this result, right? A2 is equals to 1 over e to the power 4 pi square t times e to the power t times 1 plus 4 pi square over 1 plus 4 pi square plus c. Now we will apply the initial condition to find the c. So here we can see that we have applied the condition. From here we get c is equals to negative 1 over 1 plus 4 pi squared, right? So we can write a2 is equals to this function, a simplified form, right? And then we are going to find an prime, because n prime plus n square pi square an is equals to 0, because all fn's were 0 other than n is equals to 2 and n is equals to 0. So we've already worked out for n is equals to 0 and n is equals to 2 independently. Now we are going to do for journal an, right? So an prime plus this is equals to 0, and then the initial condition is equals to negative 4 over n squared pi squared. From here we can get the solution, because this is a first order differential equation and it's homogeneous, so it's very simple. We'll apply the initial condition, we'll get c2, right plug here in the equation, and then we will generate the solution. All right, so now we are going to plug n is equals to n plus 1, because here also we are dealing with the odd numbers, right? That's why we are using 2n plus 1. So a2n plus 1 is equals to 4 to the power negative 2n plus 1 squared pi squared t over 2n plus 1 squared pi squared. Now we will construct the general solution. So the general solution is equals to a naught t plus a2t cosine 2 pi x plus the summation of this whole function, right? These are solutions that we work independently, and this is the solution that we work generally for an, right? So this is the final solution. All solutions we gathered, we added by using the superposition principle, and this is the general solution. So in this way, you can use the method of cosine expansion for the heat equation. And in the next class, we will use the Fourier expansion for the heat equation, where the boundary conditions are Robin boundary conditions, so it will generate a Fourier series, unlike cosine and sine series, right? So it depends on the boundary conditions that whatever the series is going to be generated and whatever the eigenfunction is going to be generated in the problem, right? So hope you guys will learn from this lesson. Thanks for watching the lecture. Goodbye.